Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem arithmetic slices 2 subsequence. This is definitely a hard problem, the hardest we've done in a while. We're given an integer array nums and we want to return the arithmetic subsequence. First of all, a subsequence, you're probably familiar with it. You should be if you're trying to solve a hard problem. There are a lot easier problems involving subsequences that I would probably try first if you're not. Consider an array or sequence of values. We can take a subsequence like 2, 5, 10, which is basically a subset of the values, but the order has to be preserved. That's really important. Second, for it to be a subsequence that we're actually looking for, it must be true that the difference between every adjacent pair of values is the exact same. So here you can see the difference between each of these is 2. Here you can see that all of these values are the same. So the difference between all of them is going to be 0. So that does count as well. For these, the difference I think is 4. This one does not satisfy the condition because here the difference is 0, here the difference is 1, here the difference is 3, and here it's 2. Generally, when we have subsequence problems, the main thing that we can do is make a decision of whether we want to include a particular integer or not include it, because by doing that, we form every single subsequence. Whether we choose 2 or skip it, then we can choose 4 or skip it. Here, maybe we choose 4, here we don't. This will give us every single subsequence. But what we're trying to do is count the number of subsequences that happen to have the same difference. For example, if we got here, what would we be keeping track of? We'd be keeping track of the current index, and we'd be probably keeping track of the difference as well. Because here, we don't want to continue. Like if there's a 5 up next, this subsequence doesn't mean anything to us if the difference here is 2 and the difference here is 1. So we definitely want to keep track of the difference. But as it turns out, with the recursive solution, it's actually really complicated. We're going to have to keep track of more than just these variables, and the solution is not going to be super efficient either. Normally, I really try hard to show the memoization, the recursive DFS solution before jumping into the dynamic programming solution. But this time it really doesn't make sense. I tried doing this actually, and I feel like it just made it even more confusing. So I'm actually going to skip this part, and I encourage you to do the same. But that doesn't mean we can't at least think about the idea of what is the subproblem in this case. Because the good thing here is once we've identified the subproblem, jumping into the dynamic programming solution isn't super crazy. So if we were going to solve this problem recursively, the question that we would ask is, starting at index I, how many subsequences can we get starting at index I? And to do that, what we would probably do is loop over the entire input array, looking at every value. We'd see, okay, here, there's a difference of 2. So then the question that we would ask among these adjacent pairs is, okay, how many subsequences then, starting at this number, can we get where the difference is always equal to 2? And that would kind of be the subproblem. That is kind of where the recursion would come in. Now, assuming that we ended up getting that, whatever that calculation happened to be, we would end up adding that to our result, which is like the total number of subsequences. And then we would probably do the exact same thing going to the next values, find the difference between these two values. It also happens to be 2. And then we'd ask, okay, starting from here, let's call it J, how many subsequences can we get where the difference is 2? One thing to notice is if we do it starting from this index, we already have 2 values in the subsequence so far, and then we ask from here. Oh, and by the way, I realized the difference isn't 2, it's 4. I don't know how I made that mistake. Continuing with the rest of the example, if we count the subsequences starting from here, some of the subsequences, like this one, 6 and 10, these are just 2 values. But since we know we started with an original value, we kind of guarantee that all the subsequences are going to be of at least length 3. This is just an observation to make because when I code up the DP solution, there are multiple ways to code it up. At least there's slight variations, and the main differences come in how we actually count. So this will be one way to count. There's another one I'll also show you. Okay, so we kind of know the idea of what the subproblem happens to be. And we know that at least if we were doing this recursively, one thing to keep track of would be the current index, like starting from a particular index, and second, what the difference actually happens to be. These are the main parameters. And we're going to use these when we implement the dynamic programming solution, which let me kind of show you now. So since we know these are the main parameters that we care about, I'm going to initialize this two-dimensional grid. It's actually not a real two-dimensional grid, as you're going to see in a second, but one, we have index I, which in our case is going to be 0, 1, 2, 3, 4, and we know each of these indices actually corresponds to a value. Now, for the difference, if you tried to initialize this as a two-dimensional array, you'd find that getting the difference, you'd kind of have to, like for the dimension of this, you'd have to take like the max value and the minimum value, and then probably find the difference between those. But a better way would be to instead of each of these being a row, like this looks like it's just a row, but each of these is actually going to be a hash map, because an array is kind of like a hash map, except with hash maps, we can have arbitrary key values, whereas with an array, you kind of have to have a linear sequence. So now, going through this, we were talking about with the recursive, we're starting here and then asking what's the number of subsequences starting from here with a particular difference. And that's a perfectly valid way to code up the DP solution, but it's going to require iterating through this array in reverse order, because we can't really solve this problem until we've solved this one, and we can't do that until we've solved like the smaller problem. So you'd have to go in reverse order if you wanted to think about it in terms of starting at this index. We can do it in the opposite order, where we actually take our pointer and go from left to right, which most people prefer. It doesn't really matter to me, but I'm just doing it this way because I think most people prefer it. But this way, we think of it as ending at this index. So we're finding the number of subsequences ending here, ending here, ending here, etc., etc. Okay, so now we're going to start our nested loop. Since we are doing this in reverse order, when we're here and we're trying to get the subsequences here, we have nothing to the left, so we can't really do anything. But next, when our pointer is here, then we're going to get to iterate through all of these previous ones. And let me make a note of this, because this is the most important thing. DP at index I with that diff represents the number of subsequences ending at index I with that particular difference. So now when we are at index 1, we're going to go through every previous value, kind of like I was doing when we were talking about it recursively, where if we're here, then we go through every value that's in front, but we're doing it the opposite way. We're going through every value behind index I, and then we're going to calculate the difference between these two. It happens to be 2. Okay, so what we found is that here, where index I was at 1 and the difference happened to be 2, we have one subsequence. Even though the length of this subsequence is 1, we have recorded this. So now we shift our I pointer here to 6 and we start over. So from 2 and 6, what's the difference? It's 4. So now at index I, which is currently 2, with a difference of 4, we're going to insert a 1 over here. Now we looked at 2. Next, let's look at 4. This is where it gets interesting. We find there's a difference of 2. So at index 2, where the difference is 2, what are we going to do? Are we going to just put a 1 here? Well, would that make sense? Let's look at it. We found 6, and we ensured that this subsequence has to end at this index. And we found that these two have a difference of 2. That's one subsequence. Even though the length of it is 2, it's still a valid subsequence. But we know that ending at this index, there's also one subsequence where the difference happens to be 2. Can't we use that to our advantage? Doesn't that mean that we could actually form another subsequence by including that other element? Because we know one subsequence ends here with a difference of 2. So yes, we actually can. There are 2 subsequences that are ending here, and we get that by saying 1 plus the value here, where the same difference in ending at a previous index is 2. So that's what we do, add those together and get that. Next, we shift our I pointer over here, ending at A. We do the exact same thing. Difference between 8 and 2, it's 6, so we add 6 here, And then for index 3, we put a 1 here. Next, 8 and 4. Difference is 4. So here at row 3, we are going to put a 1 here. You might be thinking, can't we just add the value up above? No, because right now we were comparing 8 with 4. 4 is at index 1. We are currently at index 3. So this is from index 2. So if we were to look up at index 1, where the difference is 4, there's nothing there. So that's why we don't add anything in this case. Next, though, it gets interesting. 8 and 6. Difference between these is 2. Now we're at index 3. So we're going to say 1 plus the value at index 2, where the difference is 2. And we get a 1 plus 2, that's going to be equal to 3. There are 3 subsequences ending at 8 where the difference between the values is 2. Want me to show them to you? This is one subsequence, this is one subsequence, and this is one subsequence. That's why we add the number of subsequences ending here to that one, because that's literally how we formed them. Now, lastly, let's get 10. We'll kind of do the same thing, 10 and 2, the difference is 8. So here we'd put a 1, and 10 and 4, difference is 6. Here, we'll also put a 1, because if we tried to look up, we'd be looking over here. And 10 and 6, that's going to be a difference of 4. We here are going to put a 1 plus, looking at 6 was at index 2, that's here, and the difference is 4. We take this one and add it as well. So here we actually get a 2 because this is a subsequence we can form where the difference is 4. Lastly, let's get 10 and 8. Difference is 2. We're at row index I equals 4. So here let's take 1 plus the value up above, which is 3, and we end up getting 4. So now that we've gone through all of that, which wasn't simple, by the way, but I'd really focus on this. This is really the entire thing. But even with all of this, what have we done? What is the problem? We've counted all of the subsequences that are of length 2 or more, but that's not what we were looking for. We were looking for the subsequences of length 3 or more. Now, here's a bit of clever math I will do. It's not super clever, but if you're familiar with like discrete math or combinatorics, it should be easy. But first, let's sum all of these together. We end up with 17, but we know we're over counting here because we included subsequences with a length 2. And in fact, when you think about it, we included every single subsequence with a length of 2, right? Because every time we took the difference between two elements, we added 1 to the hash map. Like this was included, this was included, this, and this, etc. Basically all of the subsequences of length 2. My question to you is, if we could subtract that number, which is x, we would get the number of subsequences that are of length greater than 2. So do you know a way we can, given, let's say 5 elements, how many subsequences of length 2 can we create? It's kind of a hard problem, isn't it? Because initially, like if we wanted to pick an element among these 5, we have 5 choices. So if we pick one of them, regardless of which one we pick, then we have 4 choices remaining. So if I picked 7, then I could pick 2. So 5 times 4 gives me 20. But how is that possible? 20 shouldn't be bigger than 17. Well, that's because this isn't the number of subsequences. This is the number of combinations of 2 elements. Notice, if I pick 6 first, I shouldn't be able to pick an element behind 6. But this will include that. This will include 6 and 2, as well as 2 and 6. But 6 and 2 is not a subsequence. The order matters. So what we do in this case is we take that number 20 and divide it by 2. Because if we include every subsequence twice, 2, 4, and then 4, 2, we have duplicate subsequences where the order is swapped. So we can eliminate half of those just by dividing by 2. So this is the number x that we're looking for. 7 minus 10 is going to be, or 17 minus 10 is going to be 7. That is the result of this first example if you look at the problem description. And just to quickly summarize, that formula I just did was 5, which is n in this case, multiplied by n minus 1, which was 4, and then take all that and divide it by 2. So this is how I'm going to be coding up the solution now. And by the way, as you can kind of tell from the dimensions of this, the overall time complexity is going to be big O of n squared. This is obviously n. This is the difference, and we'll have differences for every possible pair of elements, which is where that comes from. And this will also be the memory complexity. So now let's code this up. Okay, so I'm gonna initialize the result, and I'm actually also gonna initialize the length of the input because we're gonna need that in a few places. So result is initially gonna be 0, which is the number of subsequences that we're gonna return. N is just gonna be the length of the input array. And remember, when we return, we're actually not just returning the result. We are going to subtract from it n times n minus 1 and then divide that by 2. So that's ultimately what we're trying to return. So now let's go over this nested array. Well, not this nested array. Let's go over this with some nested for loops. And remember what we're trying to do. We're going through every I, and we want to consider that the end of the subsequence. So I'm actually just going to initialize dp. It's going to be an array where every value in that array is going to be a hash map. And I'm going to use a default dict in Python because it makes things convenient for us. Most importantly, let's remember what this represents. dp at index I of diff is the number of subsequences ending at I with that particular difference. So that's the most important thing to keep in mind. So now, ending at this index, we want to go through every element before that index. So we say for j in range I, and then we want to first calculate the difference between these two elements, as I've been doing. I'm going to take nums of I minus nums of j. You could do it in the other order. That's what we were doing in the drawing explanation, but it doesn't really matter because when you think about it, suppose we have 1, 2, 3, 4, 5. If we calculate it nums of j minus, and we'll take nums of I minus nums of j. Now we want to know how many subsequences with this difference are ending at index j, because 1 plus that dp at index j with this particular difference is what we're going to be adding to dp at index I with that same difference. And it might happen that this is equal to 0. It might happen that we haven't actually initialized this yet, and that's why we use a default dict in this case, because if this diff hasn't even been added to this hash map, this will return a 0 by default. So this is how many subsequences are ending at index I with this difference, and let's go ahead and add that to the result. So dp at I with this diff. And actually, this is a bug. I actually made this mistake when I was first coding this up. You want to put this line outside of this loop. Otherwise, you might end up over counting because this is not actually done yet. What if it happens that the next value that we look at also has the exact same difference? Then we'd end up incrementing this again. So we don't want to end up adding this to the result until we have calculated the final value for that. If you're still not clear why we're doing that, consider this example: 1, 2, 3, 3, 3, and then 4. We'd end up calculating like this, and then 4 and this, and then 4 and this as well. So that'd kind of be the same, and then we'd end up incrementing this multiple times. Once we've done that, we've actually solved the problem. And that is actually giving me an unassigned variable error, which makes sense if we have our diff up here. I guess one way we can actually get around this is inside of here, instead of adding this value, why not just add 1 plus this? Because that will end up accumulating in here anyway. So this should give us the same thing. Let's run it to make sure. And unfortunately, I had another bug. This should have been an addition. We don't want to assign this here because, like I said earlier, we are going to be possibly adding this multiple times to this. Again, sorry about that. And as you can see on the left, yes, it works and it's pretty efficient. Now, one more thing I want to mention, and I kind of talked about this at the beginning, you might not remember. Another way to calculate the result, actually, instead of doing this arithmetic and like getting rid of the duplicates, is here. Instead of adding to the result 1 plus this, which would include all subsequences that are of length 2 or greater, we can actually just add this part, getting rid of the 1 plus, just by adding this. This will guarantee that all the subsequences that we add to the result are actually of length 3 or greater. Because think about it this way. Here, we guarantee that at index I, there is a subsequence ending at index I where the length is greater than or equal to 2. And the count is being stored here. So when we're actually at j, and I think a better way to visualize this is probably like this. Consider we have an array, we have an element at index j, and we have an element at index I. Here, if we count something, this is clearly a subsequence of length 2 or maybe greater. But if the value stored here is positive, meaning let's say it's 1, for example, that means there was an element before j, I guess we'll call it k, that made these two form a subsequence at least of length 2. So if that count was, let's say, 1 or maybe even 4, that is the count that tells us all subsequences of length 3 or greater, because now we've added an I. So now all of the subsequences that ended here, that ended at j, should now at least be of length 3. So that's why this calculation up above works. I know it's not simple to understand. The first one was actually more intuitive for me. This one is a bit more complicated, but this one also works. I'll run it to prove it to you. As you can see on the left, it works. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.